Welcome back, Focus Learners. We've got a really fantastic explainer lined up for you today. We are literally going to look under the hood of neural networks to see what actually makes them tick. Have you ever wondered how an AI decides what information is important and what, well, isn't? Today, we're decoding a brilliant primer from Amon's AI journal, and it's all about activation functions.
To really grasp why these functions matter, let's start with a mental picture from the journal. Imagine you're working at a huge car parts manufacturing company, right? And your specific job is quality control. You check every single part coming down the conveyor belt. If it's up to standard, it moves on. If it's defective, you toss it. But what would happen if you just weren't there? Every part just moves to the next stage unchecked. What if that unchecked part was a set of car brakes? You'd end up driving a car with completely untested brakes. Nobody wants that.
Well, in the world of artificial intelligence, activation functions act exactly like that quality control operator. The process is pretty simple, but it is absolutely critical. First, a single neuron produces an output. Next, the activation function, our digital QC operator, checks that output before letting it push forward to the next layer. It essentially stands guard, ensuring only the right useful signals pass through the network.
Let's lock down a formal definition here. An activation function is a mechanism that adds non-linearity to neural networks. And here's why this is absolutely crucial. Without them, neural networks wouldn't even be special. They'd just be basic linear models. Think about it. If all we want is a linear model, standard linear regression is totally fine. Why even bother building these massive complex neural networks? The activation function is literally the secret sauce that gives AI its power to solve complex, real-world problems.
Okay, let's dive into this. Here is our roadmap for today. We just covered the AI quality control concept. Next, we'll hit the classification classics, move on to the ReLU revolution, check out how researchers fix the ReLU flaws, explore the cutting-edge activations, and finally, take a peek at the future of neural networks.
Section 2. The classification classics. These are the foundational tools used for sorting data.
Let's pit two legendary functions against each other, Sigmoid and Softmax. Now, both of these take vectors and squash them into a range between 0 and 1. But they have very specific jobs. The source gives us a great rule of thumb here. Use Sigmoid for binary tasks. Think yes or no, true or false. It applies its math entirely independently to each element. Softmax, on the other hand, is basically a generalization of Sigmoid, but it's used for multi-class classification. If you've got lots of categories, Softmax is your best friend, because it forces all the resulting elements to sum up to exactly 1. It creates this perfect probability distribution across all the classes, so the activation for one class heavily depends on all the others.
Moving right along to Section 3, the ReLU revolution.
Meet the absolute workhorse of modern neural networks, the rectified linear unit, affectionately known as ReLU. It requires less time and space complexity, mostly thanks to a cool concept called sparsity. And, crucially, it avoids the notorious vanishing gradient problem, which is when training signals get way too weak to actually teach the network anything. So, how does it work? It's wonderfully simple, actually. It just efficiently lets the output of a neuron pass exactly as long as it's bigger than 0. But if a value is 0 or less, ReLU just brutally pushes a flat 0 forward. That one simple mathematical rule adds the crucial non-linearity we were talking about earlier.
But wait, hidden right inside that beautiful mathematical simplicity is a pretty massive flaw. It's called the dead ReLU problem. Because ReLU mercilessly turns anything 0 or below into a flat absolute 0, you can end up with network elements that are completely dead, like they might never ever update with new values again. While that sparsity is sometimes a huge advantage, it can frequently cause chunks of your network to just stall out completely.
Which brings us to Section 4, fixing the ReLU flaws.
Let's break down how the original ReLU compares to its two major successors, ELU, the exponential linear unit, and leaky ReLU. Both of these fixes actually do successfully avoid the dead ReLU problem. They do this by allowing tiny gradients or creating actual small activations instead of just flatlining at 0. So, problem solved, right? Well, there's a catch. None of them, not even these new fixes, manage to solve the exploding gradient problem. Because every fix comes with trade-offs, right? Beyond that exploding gradient issue still hanging around, the journal calls out a few other cons. For both of them, the alpha value, which is a key parameter, isn't actually learned by the neural network itself. On top of that, leaky ReLU is way faster to compute because it avoids exponential operations. But during the calculus phase of training, when it's differentiated, it just becomes a purely linear function. ELU, conversely, maintains partial nonlinearity when differentiated, but all that added exponential math really increases your computing time.
So, if the classics and the fixes aren't perfect, what is next? Section 5. The cutting-edge activations.
Say hello to SELU, the Scaled Exponential Linear Unit. This thing is a powerhouse. It's self-normalizing, which means the neural network converges much, much faster. And look at that second point. With CELU, vanishing and exploding gradient problems are completely impossible. That's huge. But it's incredibly picky. It demands a very specific setup called LeCun normal weight initialization, plus a unique variant called alpha dropout. Also, it really only works well for sequential network architectures. If your network uses skipped connections, yeah, that self-normalization goes right out the window and you aren't guaranteed better performance anymore.
And then there's GELU, the Gaussian Error Linear Unit. The journal highlights a really fascinating point here. It says GELU appears to be cutting edge in NLP, particularly in transformer models. Even though it was actually introduced way back in 2016, it's recently become an absolute key player in modern natural language processing. Just like the best modern functions, it avoids the vanishing gradient problem, all while powering some of the most complex AI architectures we have today. Finally, Section 6, the future of neural networks.
So we've taken a pretty incredible tour today. From our diligent digital QC operators like Sigmoid and Softmax, through the super efficient ReLU revolution, all the way to CELU and GELU powering modern transformers. But that leaves us with the ultimate question. With all these advancements, have we actually found the perfect activation function yet? The truth from the source is clear. Every single function is just a highly specific tool. Each one has its own distinct superpowers, and for sure, each has its own kryptonite. The real takeaway here is knowing exactly what your network needs to accomplish and picking the precise mathematical operator for that specific job. So what kind of network are you going to build next? I hope this explainer gave you some clarity. Keep experimenting, keep building, and as always, keep learning.